Okay, today we're going to look at section 5.4. It's going to be on dividing polynomials. I think by the time we get to the end of section 5.4 and you've practiced it, that you're going to be a little happier. This makes what we've been doing longhand and with factoring much easier, and it simplifies things. At least I think it does. Let's look back a little bit though. First, do you remember way back when you learned how to do long division? What if we were going to divide 672 by 21? Do you remember that process? We would say 3 times 21 gives us 63. Then we would subtract. We would get 42. We would ask ourselves, how many times does 21 go into 42? We know that that's 2. And our remainder is 0. So we know that with no remainder, that that would mean that 21 that the divisor 21 was a factor of 672, which is the dividend, and that 32, our quotient, is also a factor. Now, there are several of you that may have a different model that you use for long division, and you'll just need to adjust what we're doing to it. I think it's going to work, but I'm not real familiar with it. So we can do a similar process to divide polynomials. We have our divisor, we have our dividend, and then we have our quotient. Your factor will always be your divisor, and then your expression will be your dividend. So let's set that up. And we're going to start with the same process here. What we're going to do is we're going to ask ourselves, look at the first term and ask ourselves, what do we have to multiply the first term and our dividend by to make it equivalent to the 6x squared? We're going to multiply it by 3x. Notice that here I've put the 3x above the 7x. You always line them up with whatever you're multiplying by. Since I'm multiplying by 3x to the 1, then I'm going to put it over my linear term. I'm going to do just like I did in my regular long division and multiply it out, where I get 6x squared plus 3x. Then I have to remember, and this is a very important part, you have to remember to subtract. And by subtracting, we're changing the signs, and we're going to bring down the 4x plus 2. Okay? So this is exactly the same pattern that we're using in regular long division. Now we're going to ask ourselves, what do we multiply it by 2x plus 1 by to get 4x plus 2, or at least the 4x? Multiply it by 2. When we do that, we find out that it zeroes out, and we can say that yes, 2x plus 1 is a factor of the polynomial, and that our factored form would look like 2x plus 1 times 3x plus 2. Notice the 0 allows us to assume that it is evenly divided and therefore a factor. Let's look at another example. Is x plus 5 a factor of 4x squared plus 23x minus 16? We set it up just like we did before with our dividend and our divisor. We start with 4x and get 4x squared plus 20x. Then we subtract. Then we multiply by 3. Then we subtract. We end up with negative 31. Therefore, x plus 5 is not a factor because we have a remainder. And we write our whole quotient as 4x plus 3, remainder 31. Okay, so be sure that you look at how we're noting the remainders, okay? And any remainder means that the number of the term you've divided by is not a factor. So our division algorithm, or our basic rule for this, is rather lengthy. And it says you can divide a polynomial p of x of degree by a polynomial d of x to get a polynomial q of x and our polynomial r of x. And what does all that mean? It means that we can set this up, divide d of x into p of x, our quotient, and then we have a remainder. Always remembering that if our remainder r of x is equal to 0, then we know that d of x is a factor. Okay. Important things for you to remember as we're doing this. You need to be able to include, you need to remember to include all the different exponents from the very beginning. So if you have an expression of x to the fifth plus x to the third, you need to account for the x to the fourth power. So this is an example. Is x minus 2 a factor of x minus 4 to the third? That would set up like x minus 2, x plus 4, plus 0x cubed plus 0x squared plus 0x. Notice that I have added in the 3 factors of the missing powers. I use a coefficient of 0, so I've not changed the expression at all, but you must account for every single power in descending order. Another example is x squared plus 1, a factor of 3x to the fourth plus 2x plus 3. That would set up as x squared plus 0x plus 1, a factor of 3x to the fourth, again adding the missing terms and completing the long division. You have to be sure and account for each one or your answer is not going to be right. And remember to subtract. Remember, just like in the division algorithm with all numbers, you must subtract. We use polynomial division when we're dividing by a linear factor or when we're